11th episode on aldehydes and ketones. In the today's lecture, we are going to discuss the reactions undergone by aldehydes and ketones. In the earlier lecture also, we discussed a number of named reactions like benzoin condensation, benzyl benzylic acid reaction. We discussed there this Perkin reaction and Claisen reaction, cross Claisen reaction, Dickman reaction and darzine glycidic ester reaction. So, in present lecture we are going to discuss the nucleophilic substitution in alpha beta unsaturated aldehydes and ketones. These alpha beta unsaturated aldehydes and ketones undergo two type of addition reaction, one at 1,4 position and the other at 1,2 addition reaction. We will then discuss Michael reaction and then we will discuss electrophilic substitution reaction in aromatic aldehydes and ketones. Then lastly, we will discuss the mechanism of electrophilic aromatic substitution in aromatic aldehydes and ketones. To start with the nucleophilic addition in alpha beta unsaturated aldehyde and ketone. The alpha beta unsaturated aldehyde and ketones have a double bond which is in conjugation with the carbonyl group. The resonance structure is shown like this. You can see here that this is alpha beta unsaturated carbonyl compound and these two actually are the resonance structure of this alpha beta unsaturated carbonyl compound. The nucleophile may attack either at carbonyl carbon or at beta carbon and are referred to as 1,2 and 1,4 addition respectively. Like you can see, if addition takes place at carbonyl carbon, then the product is 1,2 addition product, and if addition takes place at beta carbon here, then the addition is 1,4 addition product. 1,4 addition is also called conjugate addition in alpha beta unsaturated aldehydes and ketones. The basic reaction which actually takes place in 1,2 addition reaction is shown in this figure. We have a carbonyl group and in 1,2 addition the nucleophile comes at this electron deficient carbon and hydrogen goes to the oxygen. So, in case of 1,2 addition we get this kind of product formed from alpha beta unsaturated aldehyde and ketones. In case of 1,4 addition, the nucleophile is added to the carbon beta to the carbonyl group. The hydrogen is added to the carbon alpha to carbonyl group. Like in this case you can see that this is alpha beta unsaturated aldehyde or ketone. The nucleophile attaches itself at the beta carbon here, whereas the hydrogen attaches itself at the alpha carbon with respect to carbonyl group. We will now discuss the mechanism of 1,4 addition in alpha beta unsaturated aldehydes and ketones. In step 1, attack of nucleophile takes place onto the carbon beta to carbonyl group. You can see here this carbon is beta to carbonyl group and first attack in case of 1,4 addition takes place at this carbon. The nucleophile attacks at this carbon. As a result, there is formation of an alkoxide. In step 2, proton transfer takes place. Proton from this nucleophile goes to the oxygen or alkoxide. The addition is 1,4 addition because of the attachment of nucleophile and hydrogen at positions 1 and 4 with respect to each other. You can see that nucleophile has attached at this carbon and hydrogen has attached at this carbon. In step 3, this 1,4 addition product again you can see this is an enolic form, this is the double bond and this is the hydroxy group. So, this enolic form tautomerizes into keto form which is more stable. So, in the end if you look at the addition 1,4 addition, you can say that nucleophile has been added at beta carbon and hydrogen has added at alpha carbon, but The net result you can say is 1,2 addition, but initially the addition had taken place at position 1 and 4, and that is why this type of addition is called 1,4 addition. The 1,4 addition to alpha beta unsaturated aldehydes and ketones from reactant to product follows the route as has been given here. You can see this is alpha beta unsaturated aldehyde. What you have to do is, in case of 1,4 addition, remove this carbon carbon double bond and add 2 bonds over here. Now you have to add 1 hydrogen at the alpha carbon and add nucleophile at the beta carbon, and then you will get the final product formed in case of alpha beta unsaturated aldehyde adding at position 1 and 4. We will now discuss 1,2 versus 1,4 addition in these compounds. Actually, we have to find out under what conditions addition is 1,2 and under what conditions it becomes 1,4 addition. The nature of nucleophile largely determines the nature of addition. During the addition reaction, there is competition between 1,2 and 1,4 addition products. Strong nucleophiles like Grignard reagent favors 1,2 addition as it is a kinetically controlled reaction. Weak bases like alcohols, amines, etc. undergo 1,4 addition reaction as the reaction is thermodynamically controlled. We will now discuss some reactions where nucleophiles add at position 1,4 in alpha beta unsaturated aldehydes. First of all, we will discuss the addition of water, which is a weak nucleophile, at a beta at a alpha beta unsaturated compound. The product formed is a beta hydroxy carbonyl compound. You can see that this is alpha beta unsaturated carbonyl compound. Nucleophile has attached at beta position. As a result, there is formation of beta hydroxy carbonyl compound. Now, if instead of water we use alcohol, then alcohol again is a weak base, and instead of OH here nucleophile will be OR. The resultant compound here formed is beta alkoxy carbonyl compound. Methanol adds on to alpha beta unsaturated aldehyde and ketone in presence of sodium methoxide. Like in this case, you can see that this is a carbonyl group and this is double bond. This is an alpha beta unsaturated ketone, adds on this methoxide and produces this beta methoxy carbonyl compound. Nucleophilic reagents normally do not attack carbon carbon double bond, but it is the carbonyl function which enhances the reactivity of double bond towards such reagents. Attack of nucleophile at beta carbon produces an enolate anion which is stabilized by resonance. This is the enolate anion which is stabilized by resonance, that is both this carbon and oxygen, both of them have delta negative charge, and that is why addition can take place at either this beta carbon or at this carbon here, a carbonyl carbon. The product is formed from enolate intermediate by proton transfer to either carbon or oxygen, as has been shown in this figure. This is the enolate anion. When there is addition of proton at this oxygen, then this product is formed, and if proton comes or is transferred on this carbon, then this product is formed. Under any condition, this reaction is a faster reaction, this is a slow reaction, and after some time this 1,4 addition product is converted into 1,2 addition, this 3,4 addition, or you can say the addition has taken place at the alpha and beta next to the carbonyl group where this methanol has added. Nucleophiles which add at 1,4 position in alpha beta unsaturated aldehydes are weak nucleophile like thioalcohols. They also add on the carbon carbon double bond and forms beta thioalkoxy carbonyl compound. When primary amine adds on to alpha beta unsaturated aldehyde or ketone, then there is formation of beta alkyl amino carbonyl compounds. In case a secondary amine is used, then also there is formation of beta N dimethyl. Beta position gets the substitution of nucleophile. So, beta N dialkyl amino carbonyl compound is formed. Weak nucleophile like hydrobromic acid also adds on to these compounds, and you can see there is formation of beta bromocarbonyl compound. Potassium cyanide adds to form beta cyano carbonyl compound as has been shown in this figure. Hydrogen cyanide adds to carbon-carbon double bond of 3-butene 2-one to form 4-oxopentane nitrile, a 1,4 addition product as has been shown here. This is 3-butene 2-one. When hydrogen cyanide is added to it, then you can see that this cyano nucleophile adds on to this beta carbon here, and hydrogen goes to this alpha carbon, and that is why the product formed is a 1,4 addition product. HCN however adds to carbonyl group of 3-butenol to form 1,2 addition product also. You can see here that if this hydrogen cyanide adds on to this carbonyl group, there is formation of cyanohydrin. Now we will discuss the reaction of Gilman reagent with alpha beta unsaturated compound. Gilman reagent are lithium dialkyl cuprate which are weak nucleophile and attack the beta carbon to form beta alkyl carbonyl compound. The alkyl group being the nucleophile, the carbanion attacks the beta carbon, and there is formation of beta alkyl carbonyl compound. Lithium dialkyl cuprate reacts with 2-cyclohexenone to form 3-ethyl cyclohexanone. As you can see here, in this 2-cyclohexenone we have a double bond here. This is an alpha beta unsaturated ketone. When it undergoes reaction with lithium diethyl cuprate, then ethyl group is substituted at beta carbon with respect to carbonyl group, and there is formation of 3-ethyl cyclohexanone. Lithium aluminium hydride attacks the carbonyl carbon of alpha beta unsaturated aldehyde and ketone preferentially and forms 1,2 addition product. Here you can see that when we are using this lithium aluminium hydride, the reducing agent, addition takes place at this carbonyl group. Both the carbon and oxygen get in a hydrogen. As a result, there is formation of a secondary alcohol. Alpha beta unsaturated alcohol is formed as a result of this addition. Sodium borohydride reduces carbonyl group of alpha beta unsaturated aldehyde and ketone preferentially and forms alpha beta unsaturated alcohol, as has been seen in case of lithium aluminium hydride. So, both lithium aluminium hydride and sodium borohydride undergo 1,2 addition in case of alpha beta unsaturated aldehyde and ketones. Now, strong nucleophiles like Grignard reagent and organolithium compound attack the carbonyl carbon of alpha beta unsaturated aldehydes and ketones preferentially at 1,2 position and forms a 1,2 addition product, as can be seen in this figure, that carbonyl group has been attacked by the carbanion from this alkyl lithium, and there is formation of alpha beta unsaturated alcohol. The reaction produces racemic mixture of unsaturated tertiary alcohol as a result of 1,2 addition. You can see here that when one more alkyl group is attached at this carbon, then there is formation of a chiral center over here, and that is why in 2 enantiomers, that is both R and S isomers are formed here. We get a racemic mixture of this tertiary alcohol. Strong nucleophiles like Grignard reagent and organolithium compound, as we have told you earlier also, form 1,2 addition product. Here is in this example it is Grignard reagent forming a tertiary alcohol from this alpha beta unsaturated ketone. The reaction of methyl magnesium iodide with pent 3-ene 2-one gives 2-methyl pent 3-ene 2-one as the major product and 4-methyl pent 2-one as the minor product. Here you can see in this example, this is pent 3-ene 2-one. We have two reactive sites where the Grignard reagent or carbanion generated from Grignard reagent can attack. It is the beta carbon and this site is the carbonyl carbon. If attack takes place at carbonyl carbon, then the product is 1,2 addition product, that is 2-methyl pent 3-ene 2-ol. If attack takes place at position 1, then the product is 4-methyl pentane 2-one. We already know that Grignard reagent is a strong nucleophile. That is why the 1,2 addition product is the preferred product and is formed as a major product here, whereas the other product is formed as a minor product. If we use excess of Grignard reagent in these conditions, then instead of 2 we get 3 products. Now we will see why there is formation of one more product. Here you know already that in this molecule these are the two sites. Here the carbanion can attack and here also the carbanion can attack. If it is attacking at this position, then of course there is formation of this molecule, and if it attacks at this position, this product is formed. But if you look at this product carefully, you will find that we already have another carbonyl group present where Grignard reagent can attack, and that is why a third product is also formed if we are using excess of Grignard reagent in this reaction. We will now discuss Michael reaction. The reaction of alpha beta unsaturated carbonyl compound with compounds containing reactive methylene group in presence of a base form an addition product, and this reaction is called Michael reaction. Here you can see in this example, this is benzyl lactophenone. This is an alpha beta unsaturated ketone, and when it is reacted upon with ethyl malonate, then an addition product is formed. You can see that this part of the molecule, the carbanion, has been added at beta carbon or with respect to the carbonyl group present in the alpha beta unsaturated molecule. Michael reaction involves two carbonyl components like aldol and Claisen reaction, which are enolate and alpha beta unsaturated carbonyl compound. This one is enolate and this is alpha beta unsaturated carbonyl compound. Alpha beta unsaturated carbonyl compounds are resonance stabilized and have two electrophilic sites. As we have discussed earlier also, the two electrophilic sites here are this as well as this. The Michael reaction involves conjugate addition, that is 1,4 addition of a resonance stabilized enolate to beta carbon of alpha beta unsaturated carbonyl compound. The alpha beta unsaturated carbonyl compound is often called Michael acceptor. Michael reaction always forms a new carbon-carbon bond on the beta carbon of Michael acceptor or alpha beta unsaturated carbonyl compound. Like in this example, you can see we are starting here with this 2-methyl cyclohexanone. This generates the carbanion which attacks the beta carbon here of alpha beta unsaturated ketone. As a result, there is formation of a new carbon-carbon bond in the final product. We will now discuss electrophilic aromatic substitution in aromatic aldehydes and ketones. Actually, electrophilic aromatic substitution we have already discussed in detail in aromatic hydrocarbons. Here the only difference is that instead of hydrocarbon, that is only benzene ring or toluene ring, we have an aldehydic group, and because of the presence of aldehydic group, how the orientation changes in the aromatic ring for electrophilic substitution, that we will discuss here. Aromatic aldehydes and ketones undergo usual electrophilic substitution reaction of the benzene ring such as halogenation, nitration, sulfonation, etc. Carbonyl group is electron withdrawing, thus deactivates the ring and undergoes meta substitution. Here it has been represented with the help of these charges, that because of the electron withdrawing nature of this aldehydic group, these 3 position, the 2 ortho position and 1 para position is electron deficient, whereas these 2 meta positions are not that electron deficient. As a result, when electrophilic substitution takes place on benzaldehyde, the substituent goes on the meta position. The carbonyl group, because of minus R effect, that is minus resonance effect and minus inductive effect, behaves as a ring deactivating group, and hence it is a meta directing group. We will discuss the meta directing nature of benzaldehyde is ortho and para directing. This direction of incoming electrofield at ortho and para position can be seen with the help of these resonance structures. If you will look carefully at this structure, you will find that because of the electron attracting nature of benzaldehyde, the pair of electron or electron cloud of benzene ring is drifted towards this aldehydic group, making this ortho position, this para position, and again the other ortho position electron deficient. It is because of electron withdrawal by the aldehydic group. As a result, these benzaldehyde molecules are meta directing. We will discuss the meta directing nature of benzaldehyde with the help of these examples. Here you can see that benzaldehyde is reacting with bromine in presence of aluminum bromide. These conditions are for the bromination, and the mechanism here is electrophilic substitution reaction. Now, bromine as Br plus attaches itself at ortho position. If it attaches itself at ortho position, then you can see that we have positive charge at various positions in the ring, and you will see that positive charge are right next to each other in one of the resonance structure. In the first resonance structure, you can see that the positive charge are next to each other, which destabilize the intermediate to a greater extent. Now, when you will look at the resonance structures of benzaldehyde with meta substitution, then you will not find any such structure in these resonance structure where the positive charge is present on adjacent carbon, and also you will see that the positive charge is present at all the times either at ortho position or at para position. Now, in the third case, if substitution takes place at para position, then again we find that there is an intermediate where a positive charge is present on adjacent carbons, and this structure is especially destabilized intermediate, and that is why that actually is the reason that benzaldehyde does not undergo substitution at ortho and para position, but it undergoes electrophilic aromatic substitution at meta position. We will now discuss nitration of benzaldehyde. Benzaldehyde upon treatment with concentrated nitric acid and concentrated sulfuric acid form meta nitro benzaldehyde in very low yield. Two reasons for this. First, benzaldehyde is a deactivating group. The other reason is nitro group again when enters into the molecule is a deactivating group, and that is why a very low yield of meta nitro benzaldehyde is formed. The mixture of nitric acid and concentrated sulfuric acid which we have taken here is called nitrating mixture, normally used for nitration of molecules. We will now discuss the nitration of acetophenone, which upon treatment with concentrated nitric acid and concentrated sulfuric acid forms meta nitro acetophenone. In both the cases, that is an aldehyde or a ketone, both of them have electron withdrawing carbonyl group, and that is why both are meta directing, and that is why we get the meta substituted product. Similarly, other electrophilic substitution also comes at meta position in case of aromatic aldehydes and ketones. Now, to summarize today's lecture, we have discussed in detail nucleophilic addition in alpha beta unsaturated aldehydes and ketones. We have seen how addition takes place at 1,4 position and at 1,2 positions. We then discussed Michael reaction in detail, where addition again takes place at 1,4 positions of alpha beta unsaturated aldehyde and ketones. We discussed electrophilic substitution in aromatic aldehydes and ketones. We discussed why aromatic aldehydes are meta directing. We have discussed the mechanism of electrophilic substitution in aromatic aldehydes and ketones. In this unit of aldehydes and ketones, we have discussed the nomenclature of aldehydes and ketones in detail. We have also discussed the methods of preparation by which these kind of organic molecules can be prepared. Then we discussed a number of reactions undergone by aldehydes and ketones. As you already know that aldehydes and ketones undergo this nucleophilic addition reactions. After that, we have discussed a number of condensation reactions like aldol condensation, Cannizzaro reaction and a number of other named reaction which are very important for synthetic organic chemist. We have also discussed the nucleophilic addition in alpha beta unsaturated aldehydes and ketones, and then we have discussed electrophilic aromatic substitution in aromatic aldehydes and ketones. Hope this